Okay, so pass. Okay, yeah, appears to be working. So, in this case, I've basically backported my BGBTech3 test back to the BJX2 ISA, and I'm running it in the emulator. This is being run at an unrealistically fast speed, generally about 150 megahertz or so. So yeah, yeah, wouldn't normally be quite this fast, but pulls off decent frame rates, and it's still using software OpenGL for the rendering. Still using a fine texturing, but have slightly improved it, or improved the handling of the rendering by making by treating quads as a native type. So now it has both quads and triangles as the primitive types. In the case of quads, there's slightly less distortion from a fine warping when doing the 3D rendering. But yeah, the draw distance was set relatively small, partly for memory usage reasons and partly because at 50 megahertz has a hard time dealing with much more of a draw distance than this. This is currently about a 12-meter draw distance. Well, like for example, Minecraft typically has a much bigger draw distance than this. That's running on relatively modern and relatively fast CPUs, and also with with an actual GPU and similar, as opposed to a software renderer. Kind of makes navigating a little bit more of a challenge when one can't see more than a short distance ahead of them. As can be noted, yeah, this renderer is still using ray casting for visibility determination. So whenever a block pops in, that's because the camera has shot out a ray that hit that block, and that adds it onto the list of blocks to be drawn. The approach doesn't really scale up that well to much larger draw distances, but it does seem to work reasonably well for short draw distances. Particularly if using a relatively low ray density, which is what I ended up having to do in order to make this semi-usable. Well, I will now drop down to a lower speed. So, yeah, that's running at 157 megahertz right there. Now it's default settings, which will drop it back down to about 50 or so. So while by itself the software renderization or software rasterization is able to keep it mostly above, would be able to keep it mostly above 10 frames per second or so. The problem is that the raycast and geometry geometry rebuilding is a little bit expensive and stuff. So if it were just rendering without the geometry rebuilding or raycasting, I could probably get by with a slightly bigger draw distance than this, but this is what I have at the moment. Partly the raycasting limit is because even with a relatively low ray density, raycasting a bunch of lines out from the camera in order to see what blocks are visible does have a non-zero computational cost. And also the whole matter of blocking the list of blocks in order to rebuild all the geometry for all the blocks, which happens every few frames or so. Currently, I have it set up where it will rebuild the list of blocks every time the raycasts are redone, which yeah, at least in this setting, it's mostly able to stay, you know, within the semi-usable frame rate area, even if yeah, the draw distances are pretty awful. As for like status for the CPU ISA, not that many major new features, as things are mostly stabilizing. But oh yeah. Yeah, in terms of ISA features, nothing major new. It's still still a 3 wide BLIW with currently still with 64 registers. Well, 32 in the basic profile, 64 in the XGPR profile. In this case, like this 3D engine is built using the XGPR profile, which can help slightly with 3D rendering tasks and other stuff. Well, by having a lot more registers available for some stuff to play with, but for most normal code, it doesn't really actually make a whole lot of a difference. And some slightly newer simmed capabilities, such as a low precision floating point unit, which can be used to increase floating point performance by effectively being able to do four low precision operations per clock cycle with a 3-cycle latency. the downside of that is that it's low precision enough where I'd noted for this particular 3D engine, enabling that feature did cause noticeable geometry warping. Partly it's because the low precision floating point uses a 16-bit mantissa, and this particular 3D engine having a 64-kilometer world size does manage to, in a few cases, run into precision issues with the 16-bit mantissa. So it kind of needs full single precision in order to work. But other than that, yeah. The low precision floating point unit, or simmed unit, is however sufficient, it seems, for things like Quake. And probably it would be for this engine as well. It's just I'd have to tweak some stuff in the render to make sure that the current camera position remains always close to the origin, mostly by doing the relative local origin trick, which was used in the BGBTech3 engine, just either not implemented or not working in this engine at present. Yeah, as can be noted, yeah, the texturing, I think it's still using nearest filtering in this case. Yeah, both bilinear and nearest filtering are supported, but nearest filtering is a little bit faster, and also Minecraft used nearest filtering as well, so it sort of works. Oh yeah. Seeing it, yeah. Eventually, I did go and add integer divide instructions and similar as well. So yeah, these now are using a part of the 7 block. So for signed and modulo. Partly these were added for sake of being able to support the RISC VM like extension, but yeah, in the RISC V mode. But since I was adding it there anyways, I also added them over to BJX2 as well as an optional extension. So in this case, the molQ extension roughly overlaps with RISC V's M extension. Though even without this extension, BJX2 still has the lower precision multiplier. Just a 32-bit. So XMove for 128-bit pointers, which do technically exist but aren't really used much. These two encodings at the end here are effectively deprecated, but that's not really a recent thing. Partly it's because, you know, how how it was before, I ended up with effectively a bunch of multiple redundant possible ways to encode some of the branches, and dropping these two branch forms eliminated some of the redundancy. So I can just, you know, or just use a predicated version of a normal branch instruction to encode the conditional branches now, and leave the original condition branches as deprecated in case I want to later reclaim the space for something. Not much new in the F1 block. I did end up adding a few GBR relative loads and stores to the F2 block. Mostly these like slightly increase the efficiency of global variables, or accessing global variables for basically 32, 64, and 128-bit access, which is actually the vast majority of the global variables. So instead of being limited to the first 512 bytes of of the data segment for globals, now it's extended up to about 8K bytes, which is a little bit more range. Had added some like FP operations with an immediate value, but these aren't really used yet. Other than that, oh yeah, also a reverse subtract instruction. That's new, but not being used in this case. Results were relatively modest from this encoding, but it does seem to be non-zero at least, so that's something. Still debating whether or not it's worth actually leaving the encoding space for it, but it exists for the time being. Oh yeah, I did add some encodings that have floating point immediates, but those are 64-bit encodings. So otherwise, not that much in terms of new instructions, since there's not really that many instructions coming up at this point that actually add all that much. Around here, there is a texture load instruction, which does at least do something. At some point, I also added some BCD instructions as an experiment, which can be used for a few things, but are relatively limited in terms of their general purpose usefulness. Most in practice, like the most they could really be used for is making things like printf and similar slightly faster by like effectively offering a way to make the binary to decimal conversion faster. And other things like that. So not a whole lot new there. And yeah, texture load instruction. So yeah, the LD text instruction. This one, you give it a base. The base register contains a texture, and the index register actually contains the ST coordinates into the texture, and then it will fetch a texel. The high 16 bits of the base register are used to encode the size and format of the texture. That's used some in the software GL rendering here, which does help some, at least compared to doing it with a 5 instruction sequence for loading the block and then extracting the texel from it. Other than that, most of the recent changes have more been stuff on the software side of things and working on improving the performance of stuff compiled by my compiler. So yeah, the 3D engine works mostly, and it's mostly being in the double digits, which is it's probably like pretty okay, given that it's like, you know, still technically using software rendered OpenGL here, so yeah. And it was holding stable at 50 megahertz. And trying to scroll up to it. Yeah, in this case, spending roughly 66% of the total CPU time in the GL rasterization. This number is actually a fair bit higher than it is for Quake, because Quake seems to spend a lot more time in the Quake engine itself in things like BSP walk and other tasks like that. But in this case, it was able to achieve a whole 66% of the time spent in the GL rasterization. Fire up Doom here. So yeah, in the case of Doom now like spends time mostly above 20 frames per second. There are a few spots that were slower, like this spot here, but now this one is holding at about 16 frames per second. Don't necessarily need Doom music right now, but I did did recently fiddle with it and slightly improved the quality of the MIDI output compared to what it was before. Partly that was a case of like some of the stuff for the OPL2 configuration parameters and similar was rather poorly documented, so it was harder to figure out how to mimic it. This isn't actually directly emulating an OPL2 chip, but it's vaguely similar. Still, yeah, in this case it's, yeah, a 16-channel FM synth, so can be used as an approximate stand-in. This spot was holding at 20. This spot 23. Yeah, 23 frames per second. Drops to about 17 over here. But this is a more open area, so that's not a huge surprise. There's also some simulations running in the background. You can see that in this shot for the simulation it was running at 17 frames per second. This other shot 21. This one was 16. Simulations being, of course, massively slower than real time. So this shot was 13, a little bit slower, but that's more representative of how it would run on the FPGA version. And also Quake with its epic 4 frames per second. But getting Quake fast is one of those, or getting Quake to be usably fast is one of those easier said than done kind of things. At least on a 50 MHz CPU. But Doom is at least a little easier. Although it can be noted that there does tend to be slight discrepancy between the emulator and the the simulations and FPGA version in terms of performance. For the most part, things are like close enough where the differences can be overlooked or glossed over. Admittedly, my testing cycle on the actual FPGA has been a bit lacking recently, but partly it's because it's a little bit of a hassle to set up the FPGA to test with, but yeah, for the most part, stuff seems to still be working in my case. So at present, yeah, the CPU core does use about 71% of the FPGA budget on the XC7A100, which could be lower, but it's kind of semi-passable, I guess. Still not enough to allow dual core, sadly, but getting the resource requirements low enough to allow dual core effectively is one of those also things that's a little bit challenging. At least not without making compromises in terms of functionality. Had started working on some code for a 4-way set associative L2, but haven't finished that yet. But pros and cons there. For some things, the set associative L2 would make it faster, but generally it appears that for things like Doom and similar, they actually, or Doom seems to actually prefer direct mapped caches over the set associative caches. Not entirely figured out why that seems to be the case, but it does appear to be that things like Doom and similar seem to prefer the direct mapped caches. But yeah, terms of cost trade-offs, direct mapped caches are actually cheaper as well. So kind of why I had ended up mostly sticking with them, both for being cheaper and being similarly what programs like Doom and similar seem to prefer. So yeah. That was again running at 50 megahertz with an average of about roughly 1.3 instructions per bundle. Because I have slightly improved the bundling ratio recently as well. That was mostly a compiler thing though. Yeah, lots of fiddling and fine-tuning with the compiler. So in terms of profile, it spends most of its time, well, still in memory instructions, but branches and other stuff are making their showing as well. So, example, I guess, of what looks like fairly typical compiler output at this point. I've mostly managed to get rid of a lot of the spurious stack loads and stores. So yeah, there is generally fewer random stack loads and stores now than there used to be. Still a lot of otherwise kind of pointless, like memory moves. Albeit, yeah, those ones are setting up for a function call, so it's those ones are not spurious, but yeah. In the case where it's setting up for a function call, the move instructions are actually needed, more or less. Well, unless the compiler compiler were even more clever and could, generate results directly into the argument registers, but it's not quite that smart. We're not quite that smart yet. And maybe someday. And view of the new global related instructions, making a showing there. Yeah. This is a 64-bit encoding, which would have been a lot more common before adding the new encodings, because the new encodings can deal with the full 8K bytes of range, or 8K bytes of range, which reduces the need, or deal with that in a 32-bit encoding, which reduces the need for 64-bit encodings. In the case of an interrupt handler, as one can see, it is saving the full 64 registers, which is one of the minor drawbacks of having 64 registers. Is that, well, now you need to save and restore 64 registers, but yeah, slightly more expensive than 32. But the interrupt handlers do in fact seem to survive that onslaught of, well, more registers. Pretty sure Doom right now doesn't have well, it's not set to enable the use of 64 registers in code generation. That is now an option as well. Previously, the compiler would only use the first 32 registers for code generation and leave the remaining registers for use by assembler code, but now the compiler can use all 64 registers if it's told that it's allowed to do so. So, yeah, that's now a thing as well. But I don't think it's enabled for Doom right now, and it doesn't actually really help with Doom. Other than that, yeah, not a whole lot actually new going on with this, which is part of why updates have been slow recently. Is apart from debugging and performance tweaks, that's most of what's going on. Well, and I guess virtual memory now mostly works as well, which it didn't in the past, but now it mostly works. Still kind of experimental and not exactly 100% stable yet either, but better than it was, I guess. At least I can mostly enable virtual memory and stuff and not have it immediately explode, which is technically an improvement. So I guess that was the status update of sorts, I guess. Yep, all for now.